Hello, my name is Lila Jackson. This is my presentation on adapting simulations for the ionization and cooling of muons in particle physics through the Summer STEM Institute 2021. As you've probably learned in your science class, everything around us is composed of matter. Matter is made up of molecules, which are made up of atoms, which are made up of electrons, protons, and neutrons. Protons and neutrons are made up of even smaller particles called quarks, whereas electrons are classified as leptons, and as far as we know right now, that is their simplest form. However, when placed into a particle accelerator, electrons can be brought to high energies and collided into nuclei. This creates even more particles. These colliders have led to many discoveries in high-energy particle physics, but they produce a lot of electromagnetic radiation, which accumulates environmental damage and racks up costs. The images show a lepton collider. The solution to these issues is a heavier lepton. This is where muons come in, as they are 207 times more massive than electrons, but have almost all of the other exact same properties. Muons are formed when a proton collides into a carbon atom, which produces a neutrino and a pion. The pion is very unstable, which rapidly decays into a muon. The mice collaborators at Muon Ionization and Cooling Experiment at Fermilab have stated that if built, a future muon collider could provide 10 times the discovery reach of CERN's Large Hadron Collider even after its substantial upgrade. The LHC is the current biggest project in particle physics, but there's so much more left to be discovered to understand what is going on in the universe. In order for muons to be used effectively as a replacement for electrons in collision, they need to have a small beam. So this just means that the beam of particles must fit into the accelerator cavity. When a beam is smaller, it's considered to have a low emittance, and the lower the emittance, the better it is to fit. This emittance is written as En, and it does not change as a function of energy, allowing tracking during accelerated. So this is a normalized emittance. And a method called ionization cooling works to decrease the momentum so this normalized emittance can be restored during acceleration. Muons have a mean lifetime of only 2.2 microseconds, and the only cooling method that works fast enough to keep up this lifetime is called ionization cooling. So the particles would have decayed by the time that any other cooling method would be able to work. What I'm working on in this project is picking up where the mice experiment left off to create a more effective method of ionization cooling that can make the beam even smaller. To do this, I've used G4 Beamline, which is a particle physics simulation program based on JAUNT4, and Root, which is a CERN program for particle physics data analysis. Root actually helped with the Higgs discovery. So G4 Beamline contains some starter code simulations, and one of them was actually based on the mice experiment. So to run this, you can see the visualization above, and then the results it gathered are essentially cross sections of the beams. So the emittance starts out in the first chamber, which is right here, detected at 0.28, gets gradually smaller throughout the four, and then as you can see right here, by the fourth chamber, which is the final one in that above design, it is at about 0.15, I'm sorry. With this new cooling design I've created based on the original one, the final emittance has been able to be decreased by almost 66%. In this design, the beam of muons goes into an absorber made of liquid hydrogen encased in aluminum. In this, it is slowed down. Then it is accelerated in a radio frequency cavity with solenoids on either side. In the middle of this cavity, there is a detector which shows what the emittance of the beam is at any given moment. This goes through the same process 4 times until the beam is finally ready to be out of the cooling chamber and ready to be accelerated. To gather my data, I use this equation to measure the normalized emittance, which is again just how much space the beam is taking off. C can be organized as a matrix to show different forms of the data in a graph. The variables I have changed are the solenoid focused effect and the cooling cell focus effect, which are just controlled magnetic fields with a longitudinal field at the center and radial fields at the end, and then the ratio of the absorber material's effect on emittance, which is the material that it is passed through, so the liquid hydrogen encased in aluminum. And I also made the number of particles going through up to 1,000, just so it's easier to be understood. Right now, the current lowest emittance is 0.11 with 1,000 particle entries. Initially altering the solenoid focus current, I was able to decrease the final emittance by 47%. Here's what it would look like in the final chamber of the initial design versus the final chamber of the new design with an altered solenoid focus current. The final lowest emittance is 0.061. Next, I altered the absorber material, decreasing that emittance by almost 9%. This goes from 0.06 lowest emittance to 0.05. Finally, I altered the cooling cell focus, generating a 28.7% lower than the last emittance, so it's from 0.05 to 0.03. As you can see in this, it's color-coded, and almost all of the blue outer muons have moved towards the core where it is yellow. So our initial lowest normalized emittance, 0.01, is 65.6% bigger than our final lowest emittance at 0.039. This is a 74.49% decrease from chamber 1 to chamber 4 in this cooling design. And the reason that this is useful is just because the smaller the beam can be, the more compact the actual cooling system can be, which will in turn take up less space for the accelerator, and muons will be able to be used as an effective alternative to electrons in collision. This more effective ionization cooling design can be used in a muon accelerator replacing electrons, and also in a neutrino factory to study muon decay. My future work is this design that basically implements this cooling chamber into an entire particle accelerator. So in L, a bunch of protons are accumulated and bunched in a linear accelerator and collided into a target atom to decay into muons. Then they go through this cooling channel, which I have detailed in my previous slides, and then through a series of linear and synchrotron accelerators to bring the cooled muon beam to the energy that it needs for collision. Finally, it is able to be collided in this ring. I'd like to thank Dr. Cromaldi for assisting me with G4 Beamline and sharing new ideas and suggestions and introducing me to the local physics community. I'd like to thank Dr. Sanders for helping me download and understand the applications of Root, Dr. Kaplan for introducing me to G4 Beamline and giving me some great contacts, Savannah for mentoring me and spending time furthering my knowledge and understanding in the field, Mrs. Selwa for introducing me to the Summer STEM Institute, Ms. Bearden for encouraging me through the academic writing process in my application, Claire for mentoring me in this application process and being the first to talk to me about particle physics, Amol for initiating the challenge to reach out to professionals in the field and just share my interests, and finally Orania and Kate for making the lab groups just a wonderful experience. Thank you all for supporting